In this video, we introduced the logarithmic function as the inverse function of the exponential function. We recall that two functions are inverses of each other if they have the following action. Let's say that the function f will send x to y. Then the inverse function of f is going to undo the action of f, namely it's going to send y back to x. So in essence, whatever f does, f inverse is going to undo its action. And using this idea, we're now going to define the logarithmic function. So given a positive x value and a positive base a, also we don't allow the base to equal to 1, we define the expression log base a of x. Notice that a is written as a subscript and x is normal font. We say this expression equals to y if and only if. And now I'm going to write something in terms of an exponential expression as corresponding as an inverse function to the logarithmic function. So if and only if I have a, which remains as the base, but now the old output becomes the new input, and this equals to the old input. So in essence, if we think about in two inverse functions, what happens with their action is you interchange the input and the output. F takes x to y, f inverse will take y back to x. So what we've in essence done here with this definition for the logarithmic and the exponential function is we interchange the input and the output. Given this expression, now we can define the logarithmic function. So we say that the function f of x given by log base a of x is now called the logarithmic function base a. So let's try to now use this definition to understand what we really mean by this logarithmic expression. So now we're going to use this definition to try to better understand what does an expression like log base 2 of 8 represent. Based on this definition, log base 2 of 8 is going to equal to, let's for now write it down as question mark, if and only if, when I take its base, namely 2, and raise it to question mark, I get 8. So what does this represent? Log base 2 of 8 is going to be the number I raise 2 in order to get 8. So the log base 2 of 8 is simply a number. There's no big mystery here. And it is what number? It is the number I raise 2 in order to get 8. So let's write this down. This represents the number I raise the base 2 in order to get the input 8. So in this case, that number happens to be 3 because 2 cubed is 8. That tells me that log base 2 of 8 is 3. So again, the log of base 2 of 8 is simply a real number, and it is the number that I need to raise 2 in order to get the input 8. So now let's use this idea to evaluate some other logarithms. So let's start by looking at the log base 3 of 9. So again, this is just a number, and it is the number I need to raise 3 to get 9. And since 3 squared is 9, log base 3 of 9 is just 2. How about log base 2 of 16? To what power do I need to raise 2 to get 16? That's 4. So then this answer over here is also 4. How about log base 3 of 1? So again, the question is, to what power do I need to raise 3 to get 1? And that power is of course 0, right? Because raising a number to the power of 0 will always give me 1. So log base 3 of 1 is 0. In fact, log base any base, so base a of 1, will always give me the answer of 0. A slightly more complicated example, let's say that we're looking at log base 4 of 2. So now the question is, 4 raised to what number gives me 2? Well, the number is getting smaller. So how do I get from 4 to 2? When you have your input getting smaller than your base, you should try to think about roots. Can I use possibly a root here? And yes, it is the square root of 4 that equals to 2. So that gives me what power? 4 raised to what power gives me 2? Well, it's the fractional power that represents the root of 1/2. Similar example, let's say I have log of, say, 1,000 of 10. Again, notice that I'm going down from 1,000 to 10. So what kind of a root should I apply to 1,000 to get 10? Well, it should be the cubic root, because 10 cubed is 1,000. So the cubic root of 1,000 is 10. And therefore, the fractional power that I obtain here is 1/3. Another set of examples has to do when my input is fractional. So if I have a fraction as my input and I started off, say, with a positive integer as my base, how do I figure out what log base 10 of 1 over 100 is? Let's try to think about this first in a simple way. 10 to what power gives me 100, and that happens to be square. Now I need 1 over 100. How can I get that? By raising 10 to what power? Well, it should be a negative exponent, so it's 10 to the negative 2, because in essence I want to move the 100 from the numerator to the denominator. So when you have this fractional input, then you should think of negative exponents, and then since 10 squared is 100, the answer here is going to be negative 2. Finally, let's say I have log base 4 of, say, 1 over 64. Now, 4 raised to what power is 64? Well, 4 squared is 16, and times another 4 gives me 64, so I have 4 cubed, and therefore 4 to the power of negative 3 will give me 1 over 64, so my answer here is negative 3. So let's now deduce how to graph a logarithmic function. Well, let's focus on one example, namely, let's say we want to graph log base 2 of x. We're going to be able to deduce the graph of this logarithmic function by thinking back to its inverse function, namely 2 to the power of x, the logarithmic function, whose graph I have drawn here. And remember that the way you draw the graph of inverse functions is you can obtain one from the other one by reflecting about the line y equals to x. So what I'm going to do now is draw the line, this first bisector, y equals to x, and the way I obtain the graph of the logarithmic function is I'm going to reflect across this line log base 2 of x. So let me first draw one helping point. If this is the point of coordinates x is 0, y is 1, it's now going to turn into x is 1, y is 0. So I have that point on the graph of the logarithmic function. Now this horizontal asymptote at 0 for the exponential graph will turn into a horizontal line. So I have this piece of the graph. And then since this shoots up to infinity very fast in a concave up way, the graph here will shoot to infinity in a concave down way. And this is the graph of log base 2 of x. Again, you can see all I did was reflect across this first bisector line of equation y equals to x. So in general, the graph of a logarithmic function, when we have the base that is greater than 1, we're going to have that it goes through the point of coordinates 1 and 0, and it's going to have a vertical asymptote to the right of 0, and then it's going to shoot up to infinity relatively slowly. In fact, it has to increase to infinity very slow, because it's doing the opposite of what the exponential function is doing, which is increasing to infinity very, very fast. One special notation that is important to remember, we have two special bases. So first, if you have the base 10 to your logarithm, this is called the common logarithm, because it appears very commonly in a lot of applications. So our notation for this is going to be just log of x, as if we forgot to write the bases. It's one way to save some time with a logarithm that appears very often. So when you see that the base is missing, that just simply means it's base 10. Finally, if you have log base e of x, this Euler's number, then this is called the natural logarithm. And it's going to play a very important role in calculus, and we are going to write ln of x. So logarithm and n from natural, ln of x. It's important that we also think about the domain of logarithmic functions. You remember that when we talked about domains of functions, we introduced the condition that if you have a logarithm, whatever you have under the logarithm, so the quantity under the logarithm, can only be positive. So we set up the condition, whatever quantity you have under the log needs to be strictly greater than 0. Now we can also link that to the graph of the logarithmic function, because we can see that the log function is only defined to the right of 0, namely the domain of this logarithmic function, let's say log base 2 of x, happens to be the set open at 0 all the way to infinity, so only the right hand side of the x-axis. So let's look at some examples and try to find the domains of these functions. Let's say that I have the function f of x is ln of x minus 2. What is the domain of this function? Well, we set the condition, take the quantity under the log, and set it strictly greater than 0. Log is not defined at 0, and now you solve. We bring 2 on the other side and get x is strictly greater than 2. So the domain of this function is open to all the way to infinity, so this open interval. Let's look at a second example. Let's say I have f of x is log of 2 minus 3x. And notice, since I didn't write the bases here, I mean the common logarithm, namely base 10. So again, we have the same condition we need to set. We need to ensure that whatever comes out of 2 minus 3x, it's going to be a positive number. And now let's solve. We bring 2 on the other side and get negative 3x is greater than negative 2. And now we divide both sides by negative 3. So the right hand side, the minus and the minus cancel. You get 2/3. But remember, since we divided by a negative number, we flip the inequality sign. So the domain of this function is the interval from negative infinity to 2/3 open. So let's now look at some simple properties of logarithms, and then in the next video we'll be looking at more complicated properties of these functions. So let's start off by a simplest property, one that we already observed, namely what is log base a of 1. So in general, to what power do I need to raise a to get 1? And since that number is 0, we have that log base a of 1 is always going to be 0. Similarly, if I have log base a of a, this 2 is always going to have the same answer, namely a raised to what power gives me a? That happens to be the power of 1, so log base a of a is 1. The next two properties are a little bit more complicated and rely on the fact that the logarithmic function and the exponential functions are inverses of each other. So when I combine f and f inverse, I'm going to get back x. So if I first apply f inverse and then f, or vice versa, I'm going to end up at the same location where I started, namely at x, because the action of f inverse undoes the action of f. So the two properties are as follows. If I take the logarithmic function base a and I compose it, I plug inside the exponential function a to the x, then I get back x, just because I'm composing two inverse functions. And similarly, if I start off with the exponential function and then instead of x I replace that, I plug in the log base a of x, then again the action of f and f inverse cancel each other, and once again I end up where I started, namely at x. Finally, it's really important to try to remember the graphs of e to the x and ln of x, namely both of them base e, because they're going to play such an important role in calculus. And let's think again about their behavior, domain, range, asymptote, and end behavior. So the graph of e to the x goes through the point of coordinates 0 and 1, and because I'm interchanging the x and the y coordinates for the logarithmic graph, or the inverse function, this will go through the point of coordinates x is 1 and y is 0. So I get the graph of e to the x in this fashion, and remember we obtain the graph of the logarithmic by reflecting the graph of the exponential function across the line y equals to x, which in essence has the effect of interchanging the x and the y coordinates. So now let's think about first domain and range. What is the domain of e to the x? Well, let's just look at the graph. Nothing to memorize. You do, however, need to remember the shape of the graph. So the domain of e to the x, since the entire x-axis is being used up when I draw this graph, is the set of all real numbers, and the range, what part of the y-axis do I use up when I draw this graph? Well, only the positive part and not 0, because 0 is never attained by this function. So I have the range to be 0 to infinity. Now, for the logarithmic function, I'm going to obtain the domain and range simply by interchanging these two sets. So notice, actually looking on the graph, what's the domain of the function? I'm only using the right hand side of the x-axis. So yes, the old range becomes the new domain because I'm interchanging the y and the x. And the range, you can see I'm using the entire y-axis, so the range is the set of all real numbers, so the old domain became the new range. In terms of asymptotes, the exponential function has a horizontal asymptote, and it is a one-sided horizontal asymptote, and its equation is y equals to 0, right? The horizontal asymptote again is the x-axis, and we notice that it is one-sided, namely only as x approaches negative infinity do the function values actually approach 0. So because e to the x has a horizontal asymptote, that tells me that the logarithmic function will have a vertical asymptote, because the y now becomes an x, and it will have equation x equals to 0. So when I look at the graph to verify this, I see that this is really the case, namely the y-axis is my vertical asymptote, and what happens near this vertical asymptote, looking at the graph, as x approaches 0 from the right, and we note on the graph here that if I move and I get closer in this direction to 0 from the right, then the f of x values are approaching what? Well, what happens if I travel on this curve downwards? The y values of those points are going down to negative infinity. Finally, let's talk about what happens in this case as x approaches infinity. What happens with the f of x values, with the y values? Well, as x approaches infinity, I'm moving on the graph in this direction, and we see that the y values are shooting up to infinity. And because I'm interchanging x and y for this expression, it's not going to change anything. The same will be true for the log. As x approaches infinity, f of x also will be shooting up to infinity. So it's really easy to deduce all this information just by looking at the graphs of e to the x and ln of x, but it's really important you remember these shapes so that you can in fact deduce all this very useful information that you'll be using in calculus.